Assumptions underlying linear regression. In order for a regression to be valid, the following assumptions must hold. First of all, the relationship between x and y must be linear. To illustrate, suppose that sales is initially $100 and is expected to grow at 20% per annum. Now, if we were to plot sales, the results will be as follows. So here we are, we're starting at $100 today. And in the first year, it goes up by 20%. So at the end of the year, it'll be 120. And then from 120, it goes up another 20%. So in year 2, it'll actually be 144. And finally, in year 3, it'll go up 20%. But again, in year 3, the starting value is 144. So by the end of the year, it'll be 173. So you can see, ladies and gentlemen, when the variable, in this case sales, is growing at a constant rate, the resulting regression is not linear. In fact, it's exponential. And there it is. The relation between sales and time is not linear in this case. Instead, the linear relation is between percentage change in sales and time. And here's what we mean. If you look at the absolute value of sales, it is not constant. So we're looking at dollar sales here. You could see that it's growing by different amounts. So in the first year, it changes by $20. In the second year, it increases by $24. On the other hand, if you look at the percentage change in sales over time, it is linear. In other words, it is constant. And there it is. The percentage change in sales is 20% per year. So therefore, rather than plotting sales, we should be plotting the cumulative percentage change in sales over time. So tip, the models express percentage change in continuously compounded format. And that's the practice in the CFA curriculum, ladies and gentlemen. So when you have a percentage change, you can either express it in continuously compounded framework or using discrete framework. And again, the practice in the CFA curriculum is to use continuously compounded rates. And what discrete means is discrete is without compounding. So let's illustrate with an example. In our case, we were told that the percentage change in sales is 20% per year. So the default assumption is that this is discrete. So if it's continuous, they would actually have to come out and tell us it's continuous. So what we need to do is we need to convert from discrete over here to continuous. So there's that framework again. And so we're just going to plug in the discrete rate. So the 20% is entered as 0.20. And that's the thing, ladies and gentlemen. Most times when we're doing algebra, we have to convert from percentage to decimal. And we do that here. And then you just solve. So you take the logarithm of both sides. So the ln and the e cancel out. And over here you just have ln 120. So you just use your calculator. And your calculator will spit out 0.1823, which translates to 18.23% compounded continuously. So just to summarize what we did here, that percentage change in sales can be expressed in two different formats. So it's the same sales, but it's got two ways of presentation. Had we expressed that percentage change in sales in discrete format, it would have been 20%. But that same percentage change in sales expressed in continuously compounded format would be expressed as 18.23%. And as I indicate here, this is the one that's going to be used in practice, the continuous format. So therefore, starting from our basic linear regression right there, what we are going to be plotting now, remember we said before sales was not linear. Instead, what we're going to plot is the cumulative percentage change in sales. But again, because it's percentage change, we're doing it in continuously compounded format. So we're going to plot ln of sales, and here it is. So here's the B0 term, and this 0.1823 represents the percentage change in sales, again in continuous compounding format, per year. And let's see if we can make sense out of that. So the cumulative percentage change in sales depends on what the percentage change in sales is per year multiplied by the period in which you are in. So let's continue with our illustration. So since the initial sales at t equals 0 is 100, ln of sales, so there's my framework, right? Just got it from there. And I just have to plug in the values. So if you're looking at sales at inception, the only thing that we're going to determine here is that time would be 0, because you're looking at what sales was at inception. And at the same time, sales at that point was 100. So then what we do is we just solve for B0, because we got everything else. We've got the B1, we've got the ln of sales at t equals 0. So therefore B0 is equal to 4.60517. And there it is. So at time equals to 0, rather than plotting sales, I'm plotting the logarithm of sales. So you could see what I did here, right? We took that ln of 100 and we converted it to 4.60517. That's exactly what we got there. But now, because you're plotting the percentage change in sales, remember ln of sales, and I remind you again, this ln of sales is the cumulative percentage change in sales. And since you're plotting percentage change in sales, and the percentage change in sales is constant each year, you get the linear line, and there it is. So now we can write the entire expression for this line. So the ln of sales, which is the cumulative percentage change in sales, is equal to the intercept term, which is based on what sales was at t equals 0, plus 0.1823. And what 0.1823 is it tells you what the percentage change in sales is per year. Suppose that now we're asked to calculate what sales will be at t equals 15, so 15 years from now. So here's our framework, right there, and we just plug in the values. So we just have to plug in 15 for t. So then you solve this whole side. It's equal to 7.339. But what we want is sales, not the percentage change in sales. So then what we have to do is, we take the e on both sides, and what the e and the ln do is they cancel each other out, right? So on this side you just have sales left, but remember, whatever you do to one side, you got to do the other side. So if you're taking the e on the left side, you got to take the e on the right side. And so like I said before, the e and the ln cancel out, so then you're left with sales equal to 1,540.2. Now, just to confirm, just to prove, and you can do this yourself, what would sales have been in 15 years had we used discrete compounding? And there it is. Our initial sales was 100, growing at a discrete rate of 20% per year for 15 years would have given me the exact same answer. And that's what we have to realize, ladies and gentlemen, is that it doesn't matter which format we use, whether we use discrete or continuous. It's the same underlying sales. So your sales in 15 years is not going to be different just because you use one format versus another. Now, the second set of assumptions that must hold for us to use regression is as follows. The errors are supposed to be random. Otherwise, if the errors are exhibiting a pattern, it would imply that the model is missing something. So first, the expected or average value of the errors, otherwise referred to as residuals, must be 0. And there it is. Let's see a scenario in which the expected value of the errors was not equal to 0. Now, let me just elaborate a bit. We're not saying there's going to be 0 errors. That's not what we're saying. We're saying the average of the errors. So there is going to be errors, but if you average them out, like some errors will be above the regression, some errors will be below the regression. When you average it out, it'll equal to 0. So what would happen if the expected value of the errors was positive? It would imply that the model is underestimating the actual values. And here's an illustration. Here's an illustration. I know it seems counterintuitive. You're saying the errors were positive. How could that result in underestimation? Here it is. The red dots represent actual values. Now, if you're told that there's positive errors, that would automatically imply that the model is below it. So if you look at it from the model's point of view, the blue line represents the model, all the actual values are above it, and therefore all the errors are positive. Because that's how you measure an error. Like, look, I've done a demonstration here, but these are all errors, right? And all these errors are above the regression line, so they're positive. But if that's the case, is this model giving us an overestimated value or underestimated value of the actual values? It's resulting in an underestimation of the actual values. So I can't use this model. If a model is consistently underestimating the actual values, I'm not going to use it. And that's the theme here, ladies and gentlemen. If the errors are acting funny, we're not going to use that model. What's the second set of conditions we need to see with the errors? The variance of the errors should be constant, referred to as homoscedasticity. And here's what a good model would look like. So if you look at the variance, it's pretty consistent around the regression line. Now, if the errors if the error variance is not constant, that's referred to as heteroscedasticity, then we have a problem. So remember, the errors are not constant, or the variance is not constant. You could see over here, ladies and gentlemen, that the variance is small, like there isn't that much variability around the regression line. But look what happens as the values of x get bigger. Wow. So now you have much greater dispersion in variance. Well, isn't that sort of like a red flag? Don't you want to know, is there something happening? Why are my errors, or the variance of the errors, changing as the values for x increase? And again, if there's anything funny, you got to have second thoughts about using that model. Model becomes less reliable. Now, the third thing that we want to make sure our errors are in compliance with is the following. The errors should not be correlated to each other. In other words, there should not be any serial correlation. And here's an example of serial correlation. Have a look at these observations. They all lie below the regression line in succession. So the result is you have one negative error followed by another negative error. So they're correlated. And same thing here. You have positive errors followed by positive errors. And that's what serial correlation is, because these errors are sort of exhibiting a pattern with each other. Now, if there is serial correlation, the model is missing something, and therefore it's not reliable. Because, ladies and gentlemen, let me just show you what's going to happen if you use your model. If you use your model, your forecast for next period will be right there. Right? Because I'm just following along the trajectory. But according to the actual data, the actual value will be somewhere there. So who wants to use a model that's going to consistently give them an incorrect forecast? What is the fourth condition that we want to make sure our errors are in compliance with? The errors should be normally distributed around the regression line. So if you remember the rules of normal distribution, if your 68% band is plus or minus one standard deviation away from the mean. That's the classic confidence intervals that we're accustomed to. But now, rather than doing confidence interval around the mean, we're doing the confidence interval around the regression line. So basically, it's the same rules of thumb. So 68% of the observations will lie between plus or minus one standard error. On the other hand, if this was 1.65, so if we were looking at, so this would be, if this was 1.65, that would be plus minus 1.65. Then within this range, we would expect to see 90% of all the observations. And same thing with the 95 and 99. Now, tip, when interpreting regression results, look at the errors first. If any of the above conditions are violated, then the model is not valid. In other words, it is not reliable for forecasting.